Hello everyone, this is the second lesson of Unit 5 Process Heat Flows and treats about the problem table algorithm and the grand composite curve. The problem table algorithm is a numerical procedure that allows the calculation of the significant energy flows that cascade down the problem. These heat flows are the minimum heating that enters the problem at the tops from battery limits, the heat flows down with T, including the pinch. This is what we will call the temperature profile. And finally, the minimum cooling, the heat flow that goes out of the problem towards battery limits. And all these gonna be calculated for a concrete temperature approach. As we said, it implements the heat cascade of the problem in a way that is easily coded, and we will not need drawing the composite curves in order to calculate these flows. The next slides include a detailed description of this calculation. First, instead of real temperatures, we're gonna use displaced temperatures. We're gonna decrease supply and target temperature of every hot stream in half the minimum approach, and increase supply and target temperature for every cold stream in the same amount, the half minimum approach. In a temperature diagram, this is like rising or lowering streams, rising cold streams and lowering hot streams. In the example, stream number 1 from 200 to 100, a hot stream, goes to 190 to 90 in displaced temperature. The heat flow remains the same. And the cold stream number 4 from 40 to 100 is changed from 50 to 110. These displacements are half the minimum temperature, that is 20 Celsius. Second, we will divide the problem in displaced temperatures interval, 190, 140, and so on, placing a boundary at the supply and target temperature of every stream, hot and cold, because we don't want a stream ending or starting in the middle of an interval, just in the limits. See down here the population of a stream in the displaced temperature levels. Stream number 1 goes from 190 to 90. Stream number 3 goes from 90 to 140. Then, for the different chunk of a stream in every interval, we're gonna calculate the enthalpy balance for each interval. Some of these enthalpy calculation will be positive. This is an endothermic interval that needs heat. So some of them will be negative. This is exothermic intervals that have heat in excess. Of course, this is just a convention. And with all those enthalpies for each interval, we're gonna cascade it through the process, starting with a zero heat flows across the highest displaced temperature interval. This is the heat flow that comes from up. We're gonna calculate the heat flow across the next down interval by adding the excess of enthalpy in the interval, even if this is negative. Here, a negative 300 kilowatt heat in excess is passed down across the next limit. And in the next interval, endothermic one, the 300 kilowatts are consumed and minus 540 pass to the next interval across the limit. And so on. We will continue until the lowest boundary. The cascade in this example is not feasible because some flows are negative. It is, heat should pass from down at low temperature to up at high temperature, and this is not spontaneous. In order to make the cascade feasible, every flow must be positive. The way to do that is adding the most negative heat flow at the top. See that. The most negative flow here is minus 953. Then we're gonna take it from battery limits to the problem at the highest interval. This is the heating, 953 kilowatts. And now, as this enthalpy flow is cascaded through the different limits, then the heat that passes across each limit is increased in the same measure, and the most negative flow will coincide, and the heat flow across that interval is zero, the pinch. It is the most negative flow changed to zero. This is the pinch. Here the pinch is 90 Celsius in displaced temperature. What means that for hot stream the pinch will be at 100 Celsius, half the minimum approach up in reality, and for cold streams it will be 80, half the minimum approach down in reality. The minimum heating will be the heat flow across the top from battery limits, this 953, and the minimum cooling will be the heat flow across the bottom towards battery limits. These are the minimum heating and cooling. It cannot work with less than that. And here it finished the problem table algorithm. Without drawing, just calculating, we have the minimum heating, the minimum cooling, and the location of the pinch or pinches. Some particular cases. Multiple pinches, more than one zero heat flow can occur. And the pinch also can appear at the very top. That is, no heating is needed. This is a hot threshold problem. Or at the bottom, no cooling is needed. It's a cold threshold problem. And you must take also into account the special case of flat stream, those that doesn't change temperature. For that, normally we place a double boundary with the same displaced temperature. This is a zero width interval in temperature. Sensible heat stream, non-infinite MCP stream, doesn't contribute to this interval because this zero width temperature change. And flat stream in this interval bring all its enthalpy inside this 120 kilowatts inside the flat interval. We will finish talking about the grand composite curve, that is the temperature versus enthalpy diagram of the heat cascade, where we represent displaced T versus enthalpy flow. So this is just graphing heat flows across each boundary. And it's a very useful diagram because it shows the energy profile of the problem, where the heat flows increases or decreases. The incoming interval, incoming towards zero, in the heat flow decreases with temperature. And in outgoing interval, the heat flow increases with temperature. So one of them are enthalpy consumption regions and the other are enthalpy generation regions along the temperature change. As we will see, it is a fine tool, especially for utility design. And this is all for this lesson.